Ladies and gentlemen, we are slightly behind the schedule, so let us start. The last topic of this meeting is given by Wojciech Górny. He will be talking about geometric aspects of the least gradient problem. As a matter of fact, the least gradient problem is intimately related to geometry and analogy, because the interest in this kind of problems showed up in the 60s of the last century. And people noticed that the level sets of least gradient functions are in fact minimal surfaces. So if you wanted to find a minimal surface, it was sufficient to solve a least gradient problem, a variational problem. So after successes in the 60s, there was a period of stagnation, and I would say the main paper in this area appeared in the beginning at the beginning of the 90s, sorry, where Sternberg, Williams, Zimmer showed existence of solutions. Then another period of stagnation occurred, and it was in 2014 when Masson, Rossi, and Segura de Leon published a paper which was quite interesting and quite promising. I showed this paper to Wojciech and I told you, look, this is a cool paper, cool problem. There's a lot of things to do. Could you kindly look at it? Wojciech, after some period of hesitation, yes. I mean,
quite long period of hesitation, I would say.
And his master's thesis was quite successful because he won the first prize in the competition, A Step Toward the Future. And apparently the topic turned out so interesting that you continued. You wrote a PhD thesis. And again, the thesis was apparently successful because we meet here. And I have an impression that the topic sucked in, Wojciech got sucked in because he was somehow forced, induced, motivated to write a book. And the book is written, so maybe we'll say something about it later. And so if you have a book, and the author of the book here, so we might, and I will do, ask a question after your talk. What's left for anybody else to do in this area? But for the moment, what would you please explain the topic? The floor is yours. Thank you.
Thank you very much. Thanks for the introduction. Since the last talk of the conference, and we were slightly late, it's very good that I decided to make this talk very easy and use pictures instead of proofs. Because I want basically to convey two ideas during this talk. The first one is why the least gradient problem is different from the elliptic problems that we typically encounter. And the second one is to give some geometric insights. How can we understand this problem using simple geometric tools? This is also why I only consider the planar case. Basically, almost all the results I present here are valid in higher dimensions, but I will present it just in 2 dimensions to give a clearer geometric idea. So the starting point is the p-Laplace equation. And so for p between 1 and infinity, we can consider the following equation. So the divergence of the gradient of u to power p minus 2 times the gradient of u is 0 with some boundary condition. And if p is greater than 1, the natural space to look for solutions is the Sobolev space. So I would like to thank Michał very much for introducing a lot of notions that I don't have to do this again. So we have a function which is in LP, and it has a weak gradient in LP in a distributional sense. And to solve it, we consider an associative rational problem whose Euler-Lagrange equation is the p-Laplace equation. Okay, what we can do to find a solution of this problem, the classical tool is to use the direct method of the calculus of variations. So let me briefly say how this works and what won't work later. So we define a functional which is written here, with and plus infinity if this condition on the right-hand side is not satisfied. And it is positive, so it is bounded from below. And the main idea is that, okay, if we have a minimizing sequence, it satisfies some energy bound. From the energy bound in the functional is coercive, we can get a convergent subsequence or weakly convergent subsequence. And then the space with the boundary condition here is weakly closed. So the functional is our semi-continuous with respect to convergence. We get a function in the limit, a weak limit. This is a solution. So now, when p is equal to 1, a lot of things here don't work. Because, okay, let's write this. The first thing is that this subspace is not weakly star in this case closed. So we have two problems. One is that the limit actually might not be in W11 even. It may have discontinuities of jump type. And the other thing is that the boundary condition may not be satisfied in the limit. So the resolution to the first problem is to consider a slightly bigger space, which is the PV space. So instead of functions in L1 which have a weak gradient, which is an L1 function, we consider functions whose distributional gradient is a finite random measure. So in other words, we allow for jump time discontinuities and some other possible pathological things, but the main thing that we imagine in this case is that it is roughly an absolutely continuous part plus something with a jump. Okay, so if we now apply the direct method, what we get is a limit function which is in BV, but this subspace is still not weakly star closed. And the boundary condition may fail, so we have to be very careful in how we define the boundary condition. And here is time for 3 comments. So the first comment is that this happens whenever we have a functional linear growth. Basically, it's not related to the Lagrangian problem. If we minimize a functional with this bound, so this is bounded by a constant plus something which grows linearly in the second coordinate, we have basically the same behavior. A classical example, which was considered far earlier than the Lagrangian problem, is the area functional with the corresponding other Lagrange equation, which is the minimal surface equation. Okay, so the natural space for solutions is again BV, at least a priori, and the boundary condition has to be treated separately. And another reason, which is also considered before at least the third, both problems considered before the Lagrangian problem in the current form, is the total variation flow, which appears in image processing. So the time derivative of u is the divergence of du divided by the modulus of du, and the time-dependent minimal surface equation, where we have the same problems. But of course, what I wrote here is very suspicious. Because what does it mean? How do we understand when we write du over the modulus of du, if du is only a random measure? And basically, the problem is that if you want to understand in the most simple way that we would think of, so in the first case, you want to understand it as a random Nicotin derivative. Then of the total variation with respect to the modulus of the the gradient with respect to the total variation of measure of the gradient. Then this is defined only modulus of du almost everywhere, which doesn't mean that it's defined Lebesgue almost everywhere. But the time derivative is defined, on the other hand, Lebesgue almost everywhere. So these two things are not exactly defined on the same sets. And the classical technique from 1999, due to André Casellas and Mazon, is to replace this object by a non-uniquely defined vector field, which is called Z, which is in L infinity, with divergence which is integrable, such that we replace this object on the right hand of the equation by Z, and add a proper compatibility condition on Z, which satisfies, which comes from the equation. This compatibility condition comes from the equation. But I won't talk about this. I want to talk about something lighter. So we'll look at 2 geometric ways to look at the least gradient problem, which is the minimization problem, which is now well defined. In BV, we minimize the total variation of u given some boundary condition. So yeah, formally, this is the one Laplace equation. And this appears in relation to minimal surfaces for the following reason. If U is a characteristic function of a set which has smooth boundary, one can compute exactly what is this, and this is the minus mean curvature of E. So whenever this disappears, this means that the boundary of E is a minimal surface. So this was observed a lot of time ago in the 60s, basically. And the following result is due to the Bombieri-de-Giorgi and Giusti, that if you have a solution to the least gradient problem, the original result is a bit different, is written in a bit different way, but in a modern language, if you have a solution to the least gradient problem, then for every t, its super level set solves the least gradient problem for its own boundary data, because the super level sets have to have boundaries which are minimal surfaces. And now, if we add to this the regularity theory for area minimizing sets, which is also something which was done classically in the 70s and 80s, we can see that in 2 dimensions, every super level set has a boundary which is a locally finite union of line segments in 2 dimensions. In higher dimensions, we don't have such, there are a lot of connected minimal surfaces, they may have singularities, so the situation is not so simple. This is why I restrict myself to 2 dimensions and hide most of the difficulties in what I was doing, but I want to put the main message through. So, what is the geometric meaning of the problem? The first view is, okay, want to minimize the total variation of du. So assume that the boundary datum is a characteristic function, and assume that we are looking for solutions which are also characteristic functions of some sets. And then our problem has a very simple geometric meaning. So on the left-hand side, we have a ball. F is a characteristic function of the upper half circle. So we want to find a minimal cut such that F is exactly on one side of the cut. So we add a line segment here. This is our solution. It's very simple. It worked because the domain is strictly convex. But if the domain is not strictly convex, here, if we take the set F to be these 3 parts of the square, it's not possible. Because we would violate the boundary. If you put the whole square here, we violate the condition on the top side. So what is different with respect to the p-Laplace equation for p greater than 1? It depends on the shape of the domain, not only on the regularity, but also exactly on the shape. And the classical result, due to Sternberg and Zimmer that Piotr mentioned, is that for a strictly convex domain, for continuous boundary data, there exists a unique solution. It is continuous up to the boundary, and there are some regularity results. For instance, if omega is uniformly convex, then we recover half of the Helder regularity of solutions. But in particular, I wanted to write this result to say that not only we don't have a smoothing effect, we actually have worse regularity inside the domain than we kind of had on the boundary data usually. And the proof uses the level set method based on the result I mentioned earlier by Bombieri-de-Giorgi and Giusti. And the most difficult part is to see what happens close to the boundary. So instead of a proof or even sketch of a proof, I will present an example. Consider the boundary data. Okay, we have a ball, unit ball in 2 dimensions. We have boundary data which are very simple, which depend only on the angle. So f of theta is cosine of 2 theta. And so what do? We take any t and see that, okay, our function takes values only between -1 and 1. So let us construct the level sets by hand in this interval from -1 to 1. So let's pick some t between 0 and 1. That per image consists of 4 points, here, 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 and here. So what is the minimal configuration? We want to draw line segments connecting these points which have minimal total length. So we do this. We do this then again for all t between 0 and 1. Okay? Then we do the same thing between -1 and 1. And we end up with something looking like this. So this is basically the main idea of the solution. The main technical difficulty is that if the boundary data is not so simple, then it's not so obvious to prove that the trace is correct if we perform this construction. Okay, so now let's come to something more modern. This was done for continuous boundary data, and for a very long time, people only considered continuous boundary data. And the natural question is, can we extend this construction for this continuous boundary data? And of course, the natural idea that occurred is that what we can do is we can approximate the boundary data in an appropriate way. And the idea is that we want to construct Fn, but approximate boundary data, approximate solutions Un, which will converge to U, and we want to ensure that the boundary behavior of U is correct. So the simplest idea we could come up with
What do you want from F now?
Sorry?
So what do you want from F now? How regular is it?
Say it is just L1 function for the moment. The correct, I think the correct assumption appears in the next slide or two. Okay, so the simplest idea one can come up with is approximate Fn from below and above by continuous functions. But it is not always possible. Say we are in 2 dimensions, the boundary is 1-dimensional. Essentially, we can approximate this from above and below only if the boundary datum is in the 1-dimensional BV space on the boundary. If it's not, for instance, a classical example is that we have a characteristic function of a path-Cantor set, then we cannot make the approximation from below, and we have a problem. And actually, then the solution doesn't exist in this sense to this problem. So what we want to do is we want to construct Fn in such a way that for every continuity point of F, Fn is close to the value of F in some neighborhood. And then we want to basically construct by hand the solution locally, the solution to approximate problems locally close to this point, to ensure that we also have a similar bound for solutions in a neighborhood of x0 of the continuity point, which depends on n and shrinks with n. Yeah. And the result that comes from it, from several years ago, is that if omega is strictly convex, and if the boundary datum is continuous almost everywhere, then there exists a solution, and we have the following boundary estimate. So U is continuous at the boundary point in this sense for every continuity point of F. Okay, this result generalizes very well to higher dimensions. And one thing that I want to mention is that actually this estimate is local. So we can say that if there is a solution to an associated relapse problem, then we still have this estimate for every continuity point of F, even if we don't have a solution to the original problem. So this is basically a local estimate that you can convert then to an existence result. And so in particular, once we take this into account, and we take into account that there is the counterexample with the fat Cantor set, which has, by the way, discontinuity set of positive Hausdorff measure on the boundary. And then the trace space of possible boundary data contains continuous functions and BV functions, but is strictly included in L1. And we still don't know what is the exact trace space. And even if it is possible to find the exact trace space, because we have some results which suggest that it's not stable. I mean, under very small perturbations, we can find solutions or not. Okay, so instead of a proof, a picture. Consider very simple boundary data, that here on the left and right arcs, it is constant and equal to 1. And on the top and bottom arcs, it is constant and equal to -1. So we have 4 discontinuity points. What do we want to do? We want to approximate this using a linear function. Okay. So what we do is we approximate this with linear function, and we end up with a very similar picture to what we had before. So we construct the level sets in a similar way. Yes, here we have the linear part. Yes, we construct the level sets, and what we end up with is okay. Here are some constant regions of U, Here is a big constant region in the middle. We pass to the limit now with Fn. So these whole sectors shrink to line segments. And we end up with a solution which looks like this. So it is constant, piecewise constant, and it has 4 discontinuous at the sides of the square. Okay, and actually, this example was constructed, I mean, without proof, this example was constructed 40 years ago by Marcellini. Notice that not only this is a solution, but now, if we put in the middle a constant between -1 and 1, this is again a solution. But we didn't get this through that approximation. So, okay, one can, in this specific case, we can find a different approximation which will lead to this. But basically, the thing is that we lose uniqueness of solutions, and we lose it in a rather bad way. So we can now shift this on a set of positive Lebesgue measure. But what is the bright side of this? The bright side is that the non-uniqueness is only of this type. That we actually have uniqueness up to shifts on some sets of positive Lebesgue measure. So if omega is convex, and we have 2 solutions for some boundary datum, then they are equal except for a set on which both functions are locally constant, plus a set of Hausdorff dimension at most 1. Okay, one comment on higher dimensions. This is strictly related to the fact that we have no singularities. So this is valid in some higher dimensions, but up to dimension 7, because above we have singularities and the tree doesn't work. So a very quick sketch of proof is basically in 2 dimensions, since the levels that are line segments, whenever X lies in the boundaries of 2 superlevel sets, then these 2 things would have to coincide, except for a set of Hausdorff dimension 1, the following set of Hausdorff dimension 1, which is a jump set of one function, jump set of other function, in the sense of PV functions, plus boundaries of level set of positive measure. Okay. And in the higher dimensions, we use some maximum principle to get the first plane. Okay, so we are doing very well with time. So I want to now come to the second possible view, geometric view of the Listerian problem, which comes through optimal transport. Okay, so the Monge mass transportation problem is over 2000 years old. And in the original setting introduced by Monge, yeah, I might have overestimated a bit. Okay. So in the original formulation due to Monge, we have one measure and the second measure. Okay, this in the Monge formulation, these were measures with density with respect to the Lebesgue measure, and you want to find the map which transforms one measure to the other, which minimizes the cost which is given by the distance. So for every point x, we associated a point t of x. We take the distance between these 2 points and we integrate this over the initial measure. So a picture how it looks like in a very nice case is that, okay, we have a measure. Here we have a piece of a circle. Here we have another piece of a circle. We have some densities with respect to the Hausdorff measure, so that the picture is simpler. And to every point in the source, we associate one point in the target. We move the mass along this rays. And then very nice property, these are called transport rays, that we can associate to every point here, exactly one point here, which are joined by a line segment, which do not intersect inside except for the endpoints. Okay, but the problem is that the solution to the Monge problem doesn't always exist without an additional assumptions on the measure. Because consider the following simple example that our initial measure is a Dirac delta, and we want to split the mass into 2 parts. Then if you want to define the map T, it doesn't make sense because we don't know which point to send it to. So the classical way, due to Kantorovich, is to introduce the following relaxation. So we replace the map T by a measure on the product, which basically says that we send these points to this set. So we allow for splitting of the mass into multiple targets. So this is now, again, the cost is given again by the distance. This means that we send one measure to the other in this setting, and this is a generalized map. I mean, this is a measure which shows how we send the initial measure to the other. And then we still have some transport trace. Here, the transport, again, a long transport trace which do not intersect. And then one important thing is that we can actually see how much transport takes place in a given region. So we define a measure which is called the transport density, which encodes this, which we will use later. I won't give it. There is an explicit formula, but I won't give it. Okay. So some years ago, we noticed that actually the least gradient problem is equivalent to the Beckmann problem, which is very similar in the formulation of the least gradient problem. So we minimize the total variation of a vectorial measure with divergence 0, which satisfies a modified boundary condition. And the equivalence is given in the following sense, that from a solution to the least gradient problem, we can construct a solution to this problem. And vice versa, if the solution to the Beckmann problem gives no mass to the boundary. And the equivalence is very easy. It's formally given by a rotation of the gradient. Okay, but this problem is actually well known in optimal transport theory, because again, on convex domains, it is equivalent to the Monge-Kantorovich problem with source and target measures which are located on the boundary of the domain. Okay. And from every solution of the Beckmann problem, one can construct a solution to this problem. And the transport density, which again I won't write, is equal to the module to the total variation of the measure P. So in particular, the transport density is equal to the total variation of the gradient once we take into account the rotation, which is very nice if you want to prove some regularity results in this gradient problem. Okay. And these two things were joined together by Wojciech and Ambrosia several years ago. And basically the correspondence is like this, that the assumption that our function is in BV corresponds to the boundary datum in the Monge-Kantorovich problem to be positive measures. And the level lines of the solution in the least gradient problem correspond to transport trace. And the fact that the boundary datum is satisfied corresponds to the fact that the transport density gives no mass to the boundary, which happens automatically, for instance, on strictly convex domains. And then, well, we have some interpretation of the conditions that F is continuous, that the measures, corresponding measures are atomless. If U is in W1P, this means that the corresponding measures are in LP on the boundary. And if, sorry, this should be F. And if U is in W1P on omega, this corresponds to transport density being in LP. And what is the classical application of this technique? If I want to draw a picture, where should I draw it? Better do this here. Okay. Okay. So the classical application is like this. We have our one measure, and we have our second measure. And let's assume that the second measure is finitely atomic. Yes, this measure is in the, we're not solving the optimal transport problem. So if it's finitely atomic and this is absolutely continuous, then this is induced by a map. And actually, it's a very simple map that here a piece is moved to one point, here the next piece is moved to the second point, and so on. And these triangles, looking by which points from here go to which points in the target, are almost disjoint, and only behavior of the transport density close to these points matter for the LP regularity, because this contribution will be small. And in these neighborhoods, one can directly give the formula for the transport density, because in the optimal transport problem, it is known how the transport density looks like in this case. And we can sum up these contributions and get some estimate on the transport density. And if it's not finitely atomic, then we are very happy that this estimate does not depend on anything related to the second measure, but only to the source measure. So we can use approximations. Okay, this was maybe a bit convoluted. By using this approach, and in particular exploiting the formula, that we have a formula for the transport density, if the measure is finitely atomic, we can prove the following results. This is the original result due to Viken-Sant-Ambrogio, that if the boundary datum is in W1P on the boundary, then U is W1P inside the domain for small p. But we can also get that if F is in SBV, so it is in BV, but only has dump-side discontinuity. Okay. It is in BV, but it has no Cantor part of the derivative. Then U might be non-unique, but all solutions have this regularity. And we finally have some stability result, because none of the other methods yielded any stability results for these gradient functions, at least sufficiently general stability results. And we can get similar results for the distance, which is given by some Riemannian metric on omega. And the note on which I want to end this talk is that the equivalence extends to dual problems, and it provides a second very nice geometric interpretation of the problem. So one can compute directly what is the dual of the least gradient problem. Okay, it's something. And one can prove that it is equivalent to the well-known Kantorovich maximization problem, which is the dual of the optimal transport problem. So yeah, the solutions of this problem, the maximizers of this problem, are called the Kantorovich potentials, and they can usually be calculated explicitly, which is a very nice thing from our point of view, because the equivalence between these two problems is again given explicitly. So we can find the Kantorovich potential, and from this compute some object which gives us the structure of solutions to the least gradient problem. And again, to end with a picture, here are some boundary data for which we can find the following Kantorovich potentials. Okay. Here we now modify the boundary data in such a way that they have a discontinuity. But this constant, okay, maybe let me draw a picture. First, we consider the boundary data that we had before, which produced a square in our existence example. And now we add 4 discontinuities here. So we add 1 here and here, and we decrease by 1 here and here. Here we artificially introduce some discontinuities. The structure of solutions remain the same. The structures of the Kantorovich potential remain the same. And the picture is as follows, that the Kantorovich potential looks like this, and the solution of the least gradient problems has 11 lines like this. So we can actually prove this, that the level lines of solutions to the least gradient problems are orthogonal to the level lines of the Kantorovich potential, which actually enables us to solve the least gradient problem in a very efficient way for some given boundary data, for which we can find the explicit solutions of the Kantorovich problem.
Kantorovich potential is Brennir-McCann map?
No, because it's the Brennir-McCann map would be if we had the distance squared, and here we have just the distance. Okay, so to sum up, we have 2 complementary ways of looking at the least gradient problem from a geometric way. One is through the level sets, which are minimal surfaces, and we can study them using minimal surface techniques. And the second one, which is available only in 2 dimensions, is that we can look at the solutions to the Monge-Kantorovich problem, and the level lines are orthogonal to the level lines of the Kantorovich potential. Okay, so thank you very much for listening.
Questions?
What is on the last slide?
This picture that I made on the blackboard, so I decided to show both of them at the same time.
More questions?
It's a bit nasty question, but I was intrigued by the introduction of Celtic. somehow the problem you showed resembles the. I mean, it's not the same, but seems similar to the Eikonal equation. Like, so just because I mean, the Eikonal equation would be the.
Yeah, with the divergence of the distance. Yeah.
Yeah, exactly. So if you like programmable divergence function, you take the model of the gradient equal to some f, which is like a vector valued function, right? And then you have plenty of solutions, like really infinitely many, factored by Marcellini and the Swiss guy. So is there a connection? And something different, but
Not really. I mean, solutions to this problem are Lipschitz, at least in the sense that if you, I mean, it's a different problem because in this, I mean, at least in the versions I encountered, you have some boundary and you want to find the function g away from this. And here, in this problem, the main thing is what happens close to the boundary. So it's different.
More questions? So let me ask you the one I announced. What is left in this area after you wrote the book with Masson?
Almost everything, to be honest. For instance, the existence result says that whenever we have a boundary density which is continuous almost everywhere, then we have existence of solutions. But we have a lot of examples of functions which don't satisfy this property, and we still have existence. We don't understand it very well. What is even more annoying, one can construct, okay, if we have a slightly related problem, that here we have some different norm from the Euclidean of the gradient, and we minimize this for some boundary data. Then we can find the boundary data so that this problem has a solution, but if we very slightly perturb this doesn't have a solution. And one can even show that for C2 norms, the trace spaces are different for every norm, which is absolutely surprising because it gives no, I mean, the geometric situation is basically the same because in 2 dimensions, the minimal surfaces are still line segments, but apparently the topology changes in the boundary for sometimes that we have a solution, sometimes that we don't.
It looks to me that the catalog open problem is quite extensive. More questions?
You mentioned that in this optimal transport part, that some of the solutions are explicit.
Well, what I mentioned is that if we make this argument, then on the level of approximations, our solutions are explicit. That if we move from the least gradient problem to the optimal transport problem, we use a finitely atomic approximation, and at every level, the solution is explicit. So technically, this is a construction of a solution.
Yeah, and construction of one particular solution, right? Or is there something depending on a subsequence?
Okay, in this form that I wrote here, we assume that the source measure is in LP, so the boundary datum is in W1P, so it's continuous in 2 dimensions. So it's not surprising that we get the unique solution. I mean, this follows from the results by Sturmers, Williams, and Zimmer. But we can also extend this construction for some discontinuous cases, yeah. For initial data in SBB, or for boundary data in SBB.
So in that case, is it true that this construction somehow gives us one particular solution among a whole sea of others?
Yeah.
That's also.
More questions? If this is not the case, let us thank the speaker. Congratulate all the recipients of their awards.
That's why it's at the moment that we close the meeting. And again, thank all the laureates and all the speakers and all of you to come here to listen. And hope to meet again, especially in Łódź in September, the Spanish-Polish meeting. And maybe, not maybe, so we'll meet another meeting of third edition of the International Parliament.
I think the diplomas will be handed over in Łódź.
Hopefully, we still don't know laureates, of course,
But by that time, we yes.
Okay, then we have to additional process. So thank you again.
Gdzieś tam